Deepseek have just released on Christmas Eve V3, and it's the first time that an open source model has delivered frontier level performance. In fact, it's better than GPT-4o, and it's better than Claude Sonnet on many metrics around coding, maybe not on instruction following, but it's definitely up there among the best. And what's most amazing is it was trained for just $5.5 million if you value the compute at $2 per GPU hour. In fact, the amount of GPUs that they had available was about 2,000 H800s, whereas Meta's 405B, the most powerful open source model until now, was trained on 8 times that number of GPUs. So what's amazing is not just the performance of this model, but the fact that it's been trained on much less compute and much more cheaply. Now, if we take a look at the self-reported scores, we can just expand this graph here. You can see some metrics that understandably are the ones where Deepseek does well because they're self-reported. But this model is very strong on maths. It's very strong on coding. You can see, for example, on SWE-bench verified, this is software engineer bench. It's a test of resolving GitHub issues. The Deepseek model here is doing second best, only following Claude Sonnet, but it's beating out GPT-4o, and it's definitely beating out the other open source models like Qwen 2.5 72B and also the Llama 405B model. On Codeforce's AIME, a tough maths benchmark and math, actually Deepseek V3 is the best model of private and open source models. It performs well on GPQA Diamond, just a little bit behind Claude Sonnet, and on MMLU Pro, it's just a little bit behind Claude Sonnet and in the vicinity of all the stronger models. So in short, this model here, Deepseek V3, it seems to be the best for sure, among the best on Chinese, but even in English, it's probably the best coding and maths models, and only maybe falls behind Sonnet in terms of instruction following by a bit. We can take a look at some of the vibes. For example, if we look at some tests that people have run by themselves, there's this test here reported by Anton, and you can see he's run the Deepseek model on his own internal instruction following test. And instruction following is very important and sought after. It's probably why people like Claude Sonnet, because it follows instructions so well. And he's reporting that it scores, his test scores 51.7 on Sonnet, on Deepseek versus 64.9% on Sonnet. And I think this comment here kind of captures the general Twitter or X sentiment around the Deepseek model, which is that it's excellent. It's on par or better than GPT-4o, but not quite as good as the Sonnet 3.5 model. Now, we can also look at artificial intelligence, which is a third-party assessor of these models, both in terms of quality and speed. And in terms of quality, it's placing the model Deepseek on par with Claude Sonnet, actually, but ahead of GPT-4o. It is behind, though, the O1 models, the Mini and Preview, and presumably behind O3 as well, and O1 Pro, and it's behind the latest version of Gemini 2 Flash. When it comes to inference speeds, then, we have a speed of 77 tokens per second for Deepseek, which makes it a little bit slower than GPT-4o reported at 121, but faster than Claude Sonnet reported at 72. Now, I'm actually going to do my own speed tests here. I'm going to do them using the Deepseek API that's available at platform.deepseek.com. You can get your API keys, and if you check the docs, you can actually just hit an OpenAI style endpoint by hitting api.deepseek.com and setting your API key to the value. Now, you will need to load up a few credits if you want to test this out. The repo I'm going to use is Advanced Inference. It's a private repo that you can purchase lifetime access to. This is only a tiny portion of the scripts. It also has a lot around server setup, around setting up a RAG database using Postgres, setting up servers that can support LoRa's, and much more. I'll let you take a look at trelis.com/advanced inference if you're interested. For now, I'm going to clone that repo and open it up. I'm going to look at the API call section and the speed tests, because I want to run a speed test here on the 3 models, the Deepseek, the OpenAI GPT-4o, and Claude Sonnet 3.5. So you can see I've set some environment variables here. For Deepseek, I need to set my endpoint, my API key, and the model name, which is Deepseek Chat. For OpenAI, I set the endpoint, the API key, and the model name. And the same for Anthropic, although here I don't need to set the endpoint. It's not an OpenAI style endpoint, so I actually have to handle hitting the endpoint in my code. Now, my code is quite simple. I'm sending in a request here to generate 500 tokens. The request is a simple one. The request is to write a long essay on the topic of spring. And I run the test at a very low temperature. Not that that really matters too much. And this script here will automatically detect if Claude is in the model name and use the Anthropic client. Otherwise, it's going to call an OpenAI style client and set the appropriate API key. So I can pip install requirements in a virtual environment, and then I'll UV run VLLM and -speed.py. Now, I'm just going to check which environment variables I've set, and I'm going to unset the model just so I start fresh, and the API key, and I'll also unset the API endpoint. And now I'll just go off and check. I'll set the deep speed variables first, and we can run VLM.py. Okay, so I've just run UV run VLLM-speed.py, and we'll see the tokens per second we generate. And we're getting 44 tokens per second on this test. So let's now compare that with first GPT-4o. So I'll make the update there, unset my variables, and check my .env file. So I've set the OpenAI key, and now we'll run VLLM speed. And while we're running that, I'll just add that if you do a longer generation, say with context of 50,000 tokens, I get a speed about 16 tokens per second. And if I rerun the same query, I get about 30 tokens per second, because Deepseek does do prompt caching. So it will be faster when you make similar requests with a long prompt. Now, in this speed test, the prompt is very short, so there's not much benefit to prompt caching. So if you keep rerunning the test, you should get the same results on the same model. So I have a connection error here. Let me just try running this again. And I just reran that. I don't know what the error was the first time, maybe something with the OpenAI API, but I'm getting 72 tokens per second here. So definitely faster, as actually not quite the same numbers as artificial intelligence, but I am seeing that GPT-4o is faster. So 62 that times versus about 40 to 50 for Deepseek. So next I'm going to run Anthropic. So I'll again unset those variables and adjust my .env file. Now running on Anthropic using the Anthropic client with the same generation request. And we have 51 tokens per second. So basically Deepseek and Claude Sonnet are roughly similar in terms of speed, and GPT-4o is a little bit faster. Now this is an extremely large model. It's got over 600 billion parameters. So if you're going to run it in 8 bits, that means 8 bits per byte. So if you run it, you're going to need to download over 600 gigabytes of data, and you're going to need over 600 gigabytes of VRAM. In fact, you're going to need more because you need to store KV cache for long context. So if you're going to do this, you can try out the one-click template from my one-click LLMs repo. I would warn that it's very expensive running because you need to run on at least 8 GPUs. So it's going to cost about $30 per hour, and it takes a long time to download the weights. It can be unpredictable and take over an hour even to download the weights, including with fast transfer using HF transfer. And also it takes a long time to load the shards onto the GPU. It can take over 15 minutes. So if you're going to do this, I recommend proceeding with caution. You can fit this on either 8 H200s, or you can fit it on 8 MI300X, which is the AMD or ROCm device. But I haven't managed to get it working on ROCm. I've only managed to get it working on the NVIDIA chips. So if you're going to try that, I recommend trying 8 H200s, which may be in low supply. You would click here. You can check the template. This is the pre-built template that I have. And you can see here, it's running with SGLang. It's running the Deepseek model. I've limited the context length to 8,000 to reduce VRAM requirements, although with this much, with 8 H200s, which each have 143 gigabytes each, that's going to be well over 1,000 gigabytes. So we should have plenty of VRAM to work with. And set the tensor parallel size to 8, which is the number of machines, and then you're ready to go and deploy. So notice that if I use 8 of these at $4 per hour, it's going to be for $32 per hour to deploy this. Now I have an instance that's up and running here, and we're going to just copy this pod ID, and we're going to use it to run in the advanced inference repo, the same one I used for hitting the endpoints. And here what I need to do is I need to specify my API endpoint, which is going to be the pod ID followed by the port 8000. And then I'll need to specify my model. So I'm going to do that briefly now. Okay, so I have got that running, and I'm now going to run the same test as I did before. Rather, I've got my environment variable set. So I'm going to UV run VLLM speed, and we should be using the endpoint I've specified. So let's see if we're finding any requests on the server side. We should be. And yeah, this looks good. It looks like we're hitting the endpoint. Okay, so we have 23 tokens per second. And that's on a cluster of 8 H200s. So this really is quite slow, in fact, because the number of activated experts are 8 plus 1 shared expert, so that's 9. And in total, the number of activated parameters should be, I think, around 37,000 or something like that. So we should be seeing inference speeds that are somewhat like, that are faster than, say, Llama 70B, in fact, about twice as fast. If you look at a 30 billion parameter model, for example, in Fireworks, they're probably able to inference it at around 100 tokens per second. So you'd expect that Deepseek is able to do at least that. And in fact, Deepseek has got the ability to do speculative decoding because they have the ability to predict future tokens, even 2 tokens ahead, not just 1 token ahead. I'll talk a bit about that later, but that actually should provide a further about 1.8 times speed up because they have a very high token acceptance rate. I'll talk in more detail and explain that, but for now you can see that this is quite unoptimized, at least how I'm running it, and I would even say it's quite unoptimized how Deepseek is running it because they're getting currently around 50 tokens per second. So here, yeah, I ran it again and got 29 tokens per second. Now let's try the long context and see how that performs. Okay, so it's not going to allow me. I would have to reload the shards, and that's going to take me quite a lot of time. So I think I'll leave it at that. But you can see that this is still quite unoptimized. I know SGLang are working on it to get higher speed, but regardless, it's very hard to justify running one of these nodes yourself. Running 8 H200, it's an extremely large amount of GPUs, and to justify that, you would need to have very high number of request requirements. Now, you should be able to handle a very large load, so a very large number of customers, but I think for a lot, certainly for independent developers, you're never going to have that level of load to justify running such a large number of GPUs. And it's not a model you can just run on 1 or 2 GPUs because you need to dispatch all of the experts, of which there are 256, totaling then across the whole model about 600 billion parameters. Now, there's something interesting here. If you look carefully when we're picking a GPU, you can see that we can choose some of the larger and more recent GPUs like the H100 or even the H200, which is the larger VRAM that we needed to be able to fit this whole model. But if you look at the paper, you'll find that the paper references a different GPU, which is a H800. Now, you might think a H800 is more powerful than a H200 because the 200 is more powerful than the 100, but in fact, it isn't. And that's because the H800 was developed specifically to comply with export restrictions on sending GPUs to China. You can take a look here at the spec sheets. So for example, we have the H100 here, which was the leading GPU. The H200 is basically the same with more VRAM. It was the leading GPU before the Blackwell generation, which is the very latest generation that model builders are only starting to use. But pretty much all of the latest models, I would say, are being trained or were trained on the H100s or 200s. And there are 2 characteristics that you check. Well, there's 3. There's the VRAM, which tells you how much of the model weights you can fit. Then there is the flops. So the flops is the computing power. And if you're training in 8 bits, as Deepseek was, you could look, for example, at the 8-bit flops. So this can do 4,000 teraflops worth of computing power. And the other metric to look at is the GPU bandwidth. This is the speed with which you're able to move the weights or the parameters from the GPU into the calculation cores. So the cores that actually do the compute. You will first load all of the model weights onto the VRAM, but then the speed with which you can move from the VRAM into the calculation core, that's critical because you will otherwise be bottlenecked by how fast you can read the weights in for doing your actual calculations. So this here is 3.35 terabytes per second. Now, if you look at the H100, so just remember these numbers here. We've got 4,000 teraflops, and we've got 3.35 terabytes per second. Whereas if I look here at the H800, which is now out of production, and it says that here it's withdrawn because the export restrictions now disallow this GPU. You can see the key features here. It has an FP8 performance of 3000 teraflops. So actually this is very similar. It's only about 25% lower than the FP8 performance of the H100. And then if we look at the bandwidth, it's got 2 terabytes per second instead of 3 terabytes per second. So the main difference with the H800 is that it has about 2/3 or even a bit less of the GPU memory bandwidth. So you're able to move weights into the GPU core less fast. Now, the extent to which that affects your training performance depends on whether you are bottlenecked by the computing power or you are bottlenecked by the bandwidth. And typically during training, you have a lot of compute because you train with large batch sizes. So you train with many sequences in parallel, and this gives you a lot of computation to do. And you typically will read in the weights and do the full batch. So actually you tend not to be bottlenecked so much on the GPU's bandwidth for doing the compute. You tend to be more bottlenecked based on the number of flops. And the number of flops on the H800 are not all that much less than the H100. So even though there was some kind of export restriction, the degree to which this was binding is not necessarily very large. Although since then, the restrictions have been tightened even more so that even the H800 is not allowed. But that's what's used in the Deepseek paper. And the point that's more important than all of this is just that because of changes or improvements Deepseek have made to how they train models, they need a lot less compute. And that's the whole purpose of this video. And I want to explain in detail the tricks that they have used to basically train a model with far less compute, which means less computers and means less cost. So I'm going to do this in a few different sections. I've already shown the comparison of the models and the inference speed. I've talked about the export restrictions. And next, I'll talk about the tricks. And to understand the tricks, I need to describe, first of all, a few things about building a frontier model. I'll do that by analogy. Then I'll talk through the 3 key problems involved in the architecture they used. So basically, the overall architecture they're using is something that has been around for quite some while. Everybody uses transformers, and the specific architecture they use, called mixture of experts, has been used probably in GPT-4, but used in Mistral's model Mixtral from 2023. But it had some significant issues that meant it wasn't really being used. For example, it's not used in Llama's latest model, the 405B. And those reasons are that using mixture of experts gives you slower training. It causes issues with load balancing, so your GPUs are not equally used, which leads to just underutilized GPUs. And third of all, there are a lot of communication challenges when you're dealing with mixture of experts. So I'll explain those by a simple analogy. And then I'll talk about some of the other Deepseek tricks, like training in 8 bits instead of 16 bits, which cuts in 2 the number of memory they need, using compressed attention, which cuts the memory for long context by a factor of about 20, and then next token prediction, which improves the performance. It improves the quality of the answers. They did some ablations to measure and show that. And it also gives a platform for what's called speculative decoding, which is a way to speed up inference by a factor of about 1.8. I'll say a few things that are very technical here. I'll explain them later. But they allow for speculative decoding with an acceptance rate of about 80 to 90%, which is very, very high. In many draft model speculative decoding approaches, you get a speed up. Maybe you get 30% acceptance, 40%. You'll get higher acceptance if you're using structured context or documents like code, or maybe documents that are going to be quoted in the answer. But an acceptance rate of 80 to 90% is extremely high, and it means you can get a speed up of about 1.8 or 1.9 on your inference. So that means if you're doing 40 tokens per second, you should be doing 80 tokens per second. And to bring this back to our inference speed test from earlier, the Deepseek API is currently giving me about 43 to 50 tokens per second. Artificial intelligence shows 70. They probably measure it differently. But I think they should be able to get at least 100 tokens per second, probably even 150 tokens per second without using their speculative decoding. And with speculative decoding, I think this model should be able to get over 200 tokens per second using these GPUs. Now, I'm not taking for granted the complexity involved. You need to carefully manage these different experts. But in theory, That's the level of speed they should be able to get from this model. To understand the tricks Deepseek have found here, and they are significant tricks because they are effectively able to train the model for 10 times less than what Llama did for their 405B model. And yeah, a 10x reduction in the compute that you need. That basically means, yeah, you need way less computers, or you need to spend way less on the GPUs in order to get pretty much the same results. So this is very significant. And the question is, how did they do it? I'm going to have to go back and go through the basics here. It won't take too long. I'll do it by analogy, but I want to explain to you kind of the history of transformers over the last few years and what we have learned about how you train a frontier model. And before I go through this, I just want to say that the key to quality really is data, and having clean data that's written by experts that comes from books, for example, or internet data that's been filtered, usually using LLMs in order to pick out the best parts. And an improvement in the quality, not just quantity, is largely, well, not largely, they've both significantly led to improvements in the quality of answers you get from LLMs. And so if you think about Claude versus, say, GPT-4o, a lot of people love Claude, and it's because Claude has got really good data. They particularly have a lot of instruction following data where there'll be a request, and the language model then follows that request because of some examples they've maybe generated using PhD students or PhD graduates. So data is really key. And the fact that Deepseek's model is very good means that Deepseek have got really good data that's cleaned very well. They've probably generated some synthetically. They may have gotten experts to write examples. But because it's performing well, that tells us they have really good data. What I'm going to talk about is more the architecture. It's the design of how you set up the parameters. And this has less of an influence on quality. It does in some ways, but it mostly influences the efficiency of your model, which means the cost of running the model and also the cost of training the model. And the philosophy around how you should do this, notably the size of model you should use, has changed significantly over the years. So the analogy I'm going to use is one with books and libraries. And I'm going to compare data, which you use to train the model, to a big pile of books. And in the case of Deepseek, this would be 15 trillion tokens, which you can think of as words. So you have 15 trillion tokens. That's your data supply. And then your model, which is your matrices with weights in them, you can think of this as your library. And your compute, you can think of kind of as the heating or the operating expenses for your model. So if you have a bigger library, a bigger model, that's going to cost you more both to train, and it's also going to cost you more to operate that. Now, we can think about training, which is preparing or building the library. And then we can also think about operating the library, which is where you go and you make a query and you try and get an answer. So training you can think of as placing the books neatly in the library. Now, if the library is bigger, you're going to have to walk around all the shelves every time that you want to place a book. If the library is smaller, you'll have to walk around fewer shelves, so it'll cost you less. And you can think of the inference or the retrieval or query phase as finding the right book. So the library is built, all the books are in the shelves, and now you have a question and you walk all along the library to find the right piece of information to give you answer to that question. So this is very loosely how we can think of training. We have books and then we have a library. Now, pre-2022, where we had, say, GPT-3, which of course came on the market via ChatGPT in 2023, late 2022, we had a model with 300 billion tokens and we had 350 billion parameters in the model. So basically we had a very small, relative to today, data set and this massive model. That was GPT-3. And what developers realized is that actually this data is way too small and this model is way too big. So over the next year, we saw a shift to increase both the quality but also the quantity of tokens. So now up from 300 billion to 2 trillion tokens, if you look at something like Llama 2. So we went much bigger in terms of data and much smaller or more modest in terms of the library size. And the intuition here is that if you have a model that's just huge and has tons of parameters and you have a small amount of data, you're just not making use of those parameters and it's costing you a ton of money to run that library, it's costing you a ton of money to do the training and to do a query, because you have to retrieve, walk around all those shelves. So yeah, we basically realized we should use way more data relative to the size of the library so that the library is well utilized. And in fact, even when we got to Llama 2, it turns out the level of data was not enough. We should be using even more data relative to the size of the library. And the reason this is important is because, yes, you will put in some cost when you want to build the library and initially place those books, but that library is going to be there for years. Well, I mean, models are not around for that because they get overtaken, but they are around for some time, and you want to make it cheap for serving that model. So you have to care about not just the initial build cost, but your operating cost. And what that drives you to do is actually use a smaller library, more compact library that's going to be cheaper over time to operate. So we went even further and scaled the data up again. I can't even represent the percentage change because it's, again, another order of magnitude. But when we got to 2024, we started using even more data, so 15 trillion tokens. And you'll see this on the Phi series of models from Microsoft as well. There's just a ton of tokens that are being used because you want to pack in as much information as possible so that you have a smaller model that's cheaper to run at the time of inference. But we did see a large model as well, 405, not 450. So I'll change that here. We saw the 405 billion parameter model from Llama under the Llama 3 series. And this represents, until DeepSeek, the strongest model available. So basically the recipe as of 2024 for developing a model that's close in performance to GPT-4o or to Claude Sonnet 3.5 is to go for a very large amount of data, 15 trillion tokens, probably GPT, probably OpenAI or Google or Anthropic. They might have more tokens because they licensed more or developed more by paying people or synthetically generated more. But anyway, the recipe is lots of tokens, a pretty big model, and lots of GPUs. So for 405, there were 16,000 GPUs used over 2 months. That's at a cost of 40,000 per GPU. That's about $640 million worth of GPUs just to train that model. So you're looking at a lot of data, clean data, a very big model, and you're looking at very expensive compute because you need so many GPUs. And basically DeepSeek has come along and they've said, well, we can do all of this, but we can do it using about 1/8 of the GPUs. So DeepSeek, we can do it for about 2 months, and we can do it for 2,000 GPUs. So that's the improvement DeepSeek got. And the question is, well, how did they do that? Now, in parallel to this storyline here, where I told you about using more data, shrinking the model down for efficiency, but then increasing it again with Llama to try and compete with these state-of-the-art models like GPT-4o and Claude Sonnet. In parallel, there's another storyline, which is that of mixture of experts. So in late 2023, Mistral come out with this mixture of experts idea, which actually is in papers from Google, and there's a switch transformer paper from years before. So it's not a new idea, but it first comes out kind of in commercial use, although in open source format with Mistral in 2023. And the clever trick here is, instead of packing these books into one library, what you do is you split it into multiple libraries. And you actually have a librarian then when you make a query. So you come in and you say, what's the capital of France? And the librarian will say, well, you know, you should go to this library here. And during the training process, you have to cleverly fill the books into these libraries. And you also need to train the librarian to tell you, well, which library should you be going to when you make your request. And this is really nice because it means for a given request, your search is only going to be half the size. So you have to walk around half as many library rows in order to get the information that you need. In essence, the operating cost, so the number of GPUs, the cost to run each search, is going to be cut in half. And it's not just in half because you can actually make many libraries. You could have 4, 8, 16 libraries. I think Mistral was maybe using 8 libraries, although it would allow you to visit 2 at once for a query. So you can get this significant reduction in the size of each library, which makes each search faster. It not just makes the queries faster, it makes the training faster too. You can think of it like when you're placing a given book, instead of having to walk around all of the shelves of a massive library, you are just directed to one library and you walk around the shelves in that significantly smaller library. So this is the idea of mixture of experts. And the question is, well, if this was out in 2023, why did Meta not use the mixture of experts in its 405B model? Because it just used a very large library. Yeah, in fact, GPT-4 was kind of known or rumored at the time in 2023 to be a mixture of experts. Mistral had pioneered the mixture of experts. So yeah, why was the Llama 3 model not a mixture of experts? And the short answer is, well, mixture of experts is complicated and it has some significant drawbacks that you might not on the surface appreciate. In essence, the problem is the librarian during the training doesn't know how to spread the books evenly. And so when you're initially filling those books into the libraries, the librarian will tend to put a ton of books into one library and barely put any into the other libraries. And you end up with a system that's very unbalanced. You have, say, if you have 4 libraries here, you have one that's chock-a-block. It's stuffing so many books in, you're losing pages and you're losing some of the information, whereas the other ones are almost empty. So you're paying the full operating costs for these libraries, but they're going unused. Essentially, you kind of end up paying almost 4 times the cost for 3 things that are just mostly unused and one that's kind of overfull and losing some pages of information. That's basically what's happened with mixture of experts. It would let you, in theory, have some savings, but in practice, there would be inefficiencies because of the imbalance. To get more specific, there are actually 3 different problems that emerge. The first, I've mentioned these already, but to break them down, the first is that, yeah, you get these libraries that are just crowded, they're overcrowded, they lose pages, and that degrades the quality of answers. You have unused libraries, which is a waste of money. And the third problem is there is a lot of communication overhead, because when you're initially filling the information into these libraries, you need to know what way the other libraries are organizing their information. And this results in a need for communicating a lot, which makes the training process complicated. It means there can be delays in getting information across. And so you can't fully use your GPUs because they're so busy communicating information between each other. So the previous state of the art, it was known that this was a problem. It was known that load balancing is a big issue for mixture of experts. It's not as though Mistral or GPT-4 didn't know about this. And of course, we don't know exactly how GPT-4 solved the problem. Maybe they solved it like Deepseek, but at least we can see from Mistral, or we can see from literature, the state of the art approach for trying their best to balance. And the way that that was used to balance out during the training process, which ultimately results in better balance during the query process or the inference process. The way that this was done is by incentivizing the library to do not just one thing, but 2 things. So the standard thing you incentivize during training is for each book to be placed in the right place. What I mean by that is when you're getting a model to predict the next word, like the quick brown, and they're predicting fox, you will ask it to predict the word and you will compare it to the actual next word. So you compare fox to say dog and you will say that's wrong, so we're going to penalize. Or if the model guesses fox, you will say, okay, there's no penalty because you got the right word. So this is the standard thing to do in language model training. The non-standard thing that was being used to achieve a balance is to also incentivize the librarian during the training to spread the books evenly. So not only should the books during training go in the right place in each library, but they also should be spread somewhat evenly among the libraries so that we have roughly equal utilization. But the problem with this is when you have the joint objective, if you put insufficient weight on spreading the books, you end up with a mismatch in the libraries being loaded. But if you overemphasize the spreading of the books evenly, this distracts the librarian from putting the books in the optimal place in each library. And actually, even if you try and tune between the 2, you can never really get a trade-off. You can never get to a point where you're achieving both load balance and high quality of results. So you end up with a training process that is slower and that ultimately hurts performance, to the extent that it's hardly worth using mixture of experts. And I assume that's the conclusion that Meta came to when they decided to do their 405B model. They said, let's stick with something that's straightforward. We don't have to deal with communication. We don't deal with load balance. And we know that we won't have to do this joint objective training. We'll just focus on getting the books in the right place. So what does Deepseek do that's different? Well, they do a few things. And these are actually mentioned in literature as well. You can look back through older papers, some involving Deepseek authors and some not. But the first idea they incorporate is the idea of this shared or main library. So yes, you still have a librarian that will tell you which specialist library to look at, but you will always check additionally in this main library. And what this allows you to do is avoid duplication in libraries. It means during training, you will always have this main library that could have part of the book, and then you have the option to put some of the rest of the book in these specialist libraries. And yeah, as I said, doing this reduces duplication and it makes the specialists able to better specialize in their knowledge. So this is the first thing that was known in literature, but it's done by Deepseek. Now, the second thing that's done, and this was in a paper from August on arXiv with one Deepseek author, is to, instead of use this joint objective, so instead of telling the librarian, all right, you got to weigh both putting the books in the right place and spreading the books evenly, instead of doing that, we're going to actually adjust the librarian's recommendation. So during the training, we'll have the librarian provide a recommendation, but if the librarian recommends a specialist that is already busy, that's got a lot of processing, maybe there's a lot of staff already in that library putting books in the right place, we're going to just change that decision to go to another specialist. And this is actually done probabilistically. So if the librarian is recommending with a, say, 90% chance this specialist here, but we can see in the history that this specialist library is being used to a high percent, we're going to just decrement that probability from 90% down to 85%. And that's going to help us to load balance. And actually, by applying this somewhat manual type of load balancing, although it's dynamic, it's based on the history of which libraries are kind of busy, which GPUs or which experts are busy, we're able to avoid the librarian essentially getting confused by trying two objectives. The librarian keeps focusing on sending the request to the best library, and we then manually just rebalance to ensure that we have load balancing between the libraries. And what this does over the training is it ends up that most of the sequences are being split somewhat evenly among the libraries, and they roughly achieve the same strength. Now I'll show one or two examples from the paper here. So here I am in this paper. It's a 2024 paper from August. And you can see that there is one author at least from Deepseek, and it's called Auxiliary Loss-Free Load Balancing. And when that means auxiliary loss-free, it means you don't add in this objective for the librarian to equally balance. You just deal with it dynamically. There are two things to look at. One is the quality of the answers given, and the other is the degree of balancing of the model. You can look at the results here. So we have load balancing, we have where we have loss-free. This means we've no extra objective. We just manually or dynamically adjust the librarian's choice. And this is the original strategy that was being used up until now. You can see, first of all, the perplexity, which you want to be lower. That means that you've got better quality answers. The perplexity is very slightly lower in the case where we use this dynamic adjustment of the librarian's choice. And then if you look at the degree of imbalance, you can see the imbalance is close to 0 in this improved approach, whereas in the original approach, the imbalance is close to 1. And that means if you have on average a load of, say, 100%, when you have an imbalance of 1, it means that on average, you are a deviation of a further 100% away from that. So you will see on average, probably the GPUs have either 200% or 0%. So that's a quite large deviation in the load capacity. And yeah, basically by doing this dynamic approach, instead of confusing the librarian, you're able to get the balance down to almost perfect. So you've got almost perfect balance across all of your libraries and all of your GPUs. And furthermore, you've got an improvement in the quality of answer that you're getting because you're achieving this balance during the training. Now, there's a third aspect to mixture of experts that makes it difficult, which is if you have very many experts, you need to send information to all these different libraries. And that ends up making the training complicated. It makes the inference complicated as well. But there's a solution here. And the solution is basically to limit the number of libraries so you don't have too many. And furthermore, don't allow too many libraries to be chosen by the librarian. So I've shown you examples where the librarian is just recommending one library, but actually in practice, it makes sense to granularize, have more granular libraries, and allow the librarian to suggest a few libraries. And specifically what Deepseek does is it sets up one shared library and then 256 possible libraries that could be chosen. And it allows the librarian to pick 8 of those. But those libraries, they have to kind of be beside each other or on the same GPU to some extent. In fact, the librarian can only pick a maximum of 4 GPUs or 4 cities. You can maybe think of it as where the libraries are close to each other. And the reason for this is to limit the communication problems when you need to send information to those different libraries. So if you had to send, if the librarian was sending you to 56 libraries, that's going to be a lot of different communication trying to go and get that information. But if you restrict it to a smaller number of libraries, you're able to make sure that the communication is fairly fast and is compatible with the speed with which you can communicate between the libraries. So what can you do with these improvements? Well, basically you can get down in terms of training time or cost, and also inference or query time or cost. You can get down by a factor of roughly 8 plus 1 divided by 256. So actually there's about a factor of 30 in theory, assuming that you're splitting the information optimally. That's the kind of speed up that you're able to get. And you can think of it like, instead of walking around a 600 billion parameter book library with tons and tons of shelves, you instead, for every query, just have to walk around the equivalent of a 20 billion parameter model. So you're getting very significant savings if you're able to make this mixture of experts architecture work effectively, which it seems Deepseek have managed to do. And so, yeah, basically Mixtral realized that mixture of experts was very powerful, but at least in public literature, there weren't good ways to balance the loads. GPT-4 realized this as well. Potentially they had better ideas. I'm not sure if they had the idea that Deepseek had that's so effective around load balancing. But yeah, basically before Deepseek in public literature, the inefficiencies were kind of balancing out the benefits you got from mixture of experts. And these improvements have now changed that significantly. And now for the 3 final tricks I'll describe as part of the Deepseek paper. First of all, using 8 bits of training instead of 16. Second of all, using what's called compressed attention, or latent attention as the Deepseek paper V3 calls it. And last of all, next token prediction, which allows for improved quality answers, and it provides a pathway for faster inference by about 80% faster. Training in 8 bits is the easiest one to describe. Quite simply, instead of representing each model parameter, you represent it, instead of 16 bits, you represent it in 8 bits. And this is possible because the last generation of GPUs that start with a H, that's H for Hopper, as in Grace Hopper, the scientist, the Grace Hopper architecture allows you to run in 8 bits. So it allows you to do multiplications of 8-bit numbers by each other. Previous generations like Ampere or the T4, say the A100s or the T4, they do not allow for 8-bit multiplications. They only support 16 or 32 bits for multiplication. So this is one of the first models that we know is leveraging 8-bit multiplication. Now, maybe GPT-4 was, or GPT-4o, maybe some of the Anthropic models are, because the computers support that if they're trained on H100s or H200s. But of course, those details aren't public. Now, it's not trivial to just move to 8-bit instead of 16-bit representing your weights, because 8 bits has less precision. It has less bits available to describe that given number. And so if you just naively swap to using 8 bits, you can run into precision issues that cause your model to train more slowly or to be unstable. And one of the reasons for that is if you multiply 2 numbers that are each 8 bits, and you then multiply 2 other numbers and you take a difference between the two, often that difference can be very small. It can be smaller than is represented by your 8 bits. And those errors can propagate because essentially any number you get from that calculation is either rounded down or rounded up. And the solution to that employed by Deepseek is to temporarily store some of the results in 16 bits or in 32 bits. And by temporarily doing this, you're able to ensure that intermediate states don't lose their precision. And when you get to the final result, you can, yes, store it again in the reduced 8-bit precision. So that's a brief description of the 8-bit approach, and it allows them to essentially get twice the amount of processing power from the same computers, or said differently, it cuts roughly in half the number of GPUs that they would require. Now, the second approach they use is compressed attention, and this is actually not new. It's in Deepseek V2 as well. And what compressed attention does is allow them to process long sequences of training text or long questions at inference time with much less memory. Now, to understand how compressed attention works, you first need to understand attention. And to understand attention, you need to understand how a GPU, or rather how a transformer works. And LLMs, or transformers, because that's the architecture that LLMs use, they're all about next word or token prediction. For example, the quick brown, and then we're trying to predict the word fox. And to do this prediction, we split the question or the input text into tokens or words. And those words are then represented as numbers or vectors. So you might have a word brown and it's represented by a vector here in 4 dimensions going this way. In practice, it would be maybe 1,000 dimensions or something very large. And the way transformers process these numbers is in 2 ways. First of all, they will consider the previous word. So in order to predict the word fox, they will look at the word brown. But transformers also look at the pairwise relationships between previous words. So if you look at the quick brown fox, or the quick brown, the transformer will consider the pairwise relationship between the and quick and brown, and the and brown. And in order to make this pairwise process efficient, it's common to store information on the history. And actually, it's not the pairwise relation. I mean, it is and it isn't. It depends if you talk about what you're doing at each layer. But suffice to say, it's more efficient if you store the historical pairwise information, because you are auto-regressively generating or predicting each next token. So as you predict the word fox, you've stored the pairwise relationships for the quick brown, and the brown. And then when you want to predict the next word beyond fox, which would be jumps, you already have stored these pairwise relationships. And so you avoid having to do some recomputation. And this storage involves storing effectively the name. You can think of it as the name, like the name tag of a given token, and a little message that the token has for you. So they are called keys and values. So you have a key, which allows the model to identify that token, and you have a message, which is some information that token is bringing to the model. And these are both derived from the representation of the token, which I said earlier is a vector. So you have brown represented by 4724. And then derived from brown, you have a key or a name, you can think of it as, that allows the model to identify and find that token. And then you have a message that the token is effectively going to send or provide to the model, which again is derived from the representation here. And what I'm saying is this is what's called attention. It's the consideration of pairwise relationships that is done using the keys and messages. Now, these keys and values are going to be stored so that when we calculate them once, every time we auto-regressively get a next token, we can just reuse some of those keys and values. And quite simply, compressed attention is the idea that instead of storing the full key or the full value, we'll store a compressed form. So instead of storing for the key 5722, I mean, this is a naive form of compression I'm doing here. I'm just kicking out the last 2 numbers. I'm just going to store 5 and 7. Or instead of storing 3991, I'll just store 3 and 9. Now, in practice, you do better than just kicking off some dimensions like I've done. Think of it more like if you see a car on the street and then you paint that car in 2D. Well, your painting is a representation of an object that's in 3D. So you've projected the car down into a 2D painting. And it's a similar approach as to how you store the compressed keys and values. You take a high dimensional key, like 1,000 dimensions, and you project it down into a lower dimension, maybe like 10. And actually, it's a very significant compression. It's probably by a factor of at least 20 that this allows information to be compressed. And what is interesting, and maybe not necessarily obvious, is that you can do this without really affecting performance. So that's one of the major insights Deepseek had in their V2 paper. You can basically compress these keys and values, which you can think of as name tags for the tokens, and you can save by a factor of about 20 on storing historical information. And because you can store historical information in a compressed way, this allows you to now process much longer sequences, maybe 100,000 in length, for example. So yeah, that's why this is useful. It saves them. It saves the memory required in order to run longer sequences, and this means they need less GPUs when they're running longer sequences. Now, I will take a very quick look at the paper just to show you some of the ablations. So here we can look at the Deepseek V2 paper. And this is a little bit more technical what I'm going to say here, but I'm going to say it for the benefit of those who are familiar with attention. I'm going to look at the comparison of the key value cache, and I'm going to try and find here a graphic explaining the method. And actually, compression is something that has been used, and it's already typically used in transformers, but the method of compression is not as efficient as what Deepseek use. So traditionally, starting from maybe the earliest transformer, you would have a key or a name tag that has a message, so it has a value for every single token. So you have keys and values for every token, and they are all individual. But storing a key and a value with dimension 1000 each requires a lot of memory. So people said, well, why don't we make them grouped? So we'll still give them individual keys and values, but the matrices we use to derive the keys and values from the input vector, we will share those. And that's grouped query attention. You basically share the generation method in groups. So it's not entirely shared, but it's partially shared. And then you've multi-query attention, where they're completely shared. So the matrices you use to generate keys and values, they are shared amongst all the keys and all the values. Doesn't quite save you memory in storing the keys or values, but it at least allows you to reduce the number of matrices that are required to generate those keys and values. So it's a form of compression that achieves a slightly different kind of saving. It's actually a compute saving as opposed to a memory saving. Whereas the way Deepseek go about it is they say, okay, we're actually going to allow keys and values to be derived separately, but we're going to compress the keys and values once they are formed, so they are much smaller than the dimension they typically would take. And it just turns out, this is not necessarily obvious, but it turns out that you can compress these keys and values almost losslessly by a pretty large factor and get similar performance. And actually, because you can compress them by so much, you can kind of afford to use more parameters in other places that you otherwise might not have. And what this allows Deepseek to do is actually get a model that performs better in terms of quality, even though it requires way less memory, because they found that actually you need far less parameters in order to store the keys and values while maintaining the quality to a large degree. And they run some ablations here. I can maybe find, if I go back up to the top and I search for some ablations, I think maybe in the appendices. So ablation of these methods here. And their method is called MLA, which is for latent attention. And you can see if you look at the MLA versus multi-head attention, you're able to get performance that is higher. So higher is better on all these benchmarks, and it is meaningfully higher both for small and for large models. And they also show an ablation here of the three kind of traditional methods: the multi-headed attention, which is granular, versus the grouped query attention, and versus the multi-query attention. And you can see how multi-head attention gets the best performance here, but it requires many more parameters. You can see in the large model, the KV cache per token is 860,000 versus just 34,000 when you use this latent attention method that compresses the Ks and the Vs. And again, just to state that the performance improvement here is largely because you are now, because you have such compression, you can afford to use extra parameters in your other dimensions where they do impact the quality. Essentially, it turns out you're better off not doing too much sharing. So sharing is kind of bad in that it reduces performance, but you can afford to do less sharing if you are doing the compression of the KV cache as Deepseek do. So that's the compression. And moving on to the third method that is quite novel, I haven't seen it before, we'll talk about next token prediction. And really, I should say here, we'll talk about next token prediction, because next token prediction is how language models work. You have a phrase, you try and predict the next token, you penalize the model based on whether it gets that right or not, and you update the parameters. Now, this is very effective. It has allowed the whole generation of GPT-type models to emerge, and probably everything that's out there today only does next token prediction. Now, maybe OpenAI or Anthropic do next token prediction, but this is the first time I've seen it. Now, in theory, if you only penalize the model during training based on the next token, you're kind of leaving some money on the table because there is information in the following tokens that come on afterwards. Now, this requires a slightly different architecture, but if you can find a way for a model to, at the same time, and I don't mean auto-regressively because we already do that, I mean at the same time predict not just the next token, but the following ones, you can actually penalize the model based on those future tokens too. And in principle, this gives you extra information that should improve the speed and quality of your training. So let's take a look at how Deepseek does that. It's in the V3 paper, which I'll open up here, and I can scroll down to the multi-token prediction. And the easiest way to think about it is via this chart here, which shows a traditional transformer. So you have tokens coming in, they get converted to vectors, and then they go through multiple layers where these matrices run attention. So they'll look for the name tags of the previous tokens, and they will also run multiplications with matrices to try and transform the input vectors into an output prediction. So this is the next token prediction here. But now there are actually new blocks that are not traditionally within transformers. And the purpose of this new block, and it's just a single block compared to what is probably 60 to 100 blocks that are typically here in the main transformer. This new block here has a new purpose, which is to take the next token prediction and make a prediction for the next token. And this module here, which is called module 2, this is predicting the next token. And the idea is that you penalize the model not just traditionally based on the next token, but on these future tokens as well. Now, Deepseek, actually, when they implement the model, they only go 2 tokens ahead. So they look at the next and the next token. They could look at one further ahead, but they don't. They do an ablation. So they compare what happens if we actually run this versus if we don't include it. And the ablation shows that they are getting better performance if they add this multi-token prediction. So let's go ahead and check that. If we go to the appendices, let's see, there should be an ablation here for looking at next token prediction, multi-token prediction. Yeah, multi-token prediction evaluation. And here we have the ablation studies for multi-token prediction. And this is done on both small models and large models. Sorry, let me move down to where those results are. Yeah, the small model, the large, with baseline and with the multi-token prediction. And you can see significant improvements. For example, MMLU goes from 50 to 53 on the small model, and it actually goes down slightly here when we add MTP on the large model, but pretty much all of the other tests go up in terms of score. So it seems fairly convincing that adding MTP, as theory suggests, improves the quality of the model's predictions. And the reason is because if you are predicting on the basis only of the next token, you are ignoring the fact that that next token may give rise to very improbable tokens on the next token. For example, if you pick some token like door, I'm just saying this may not be a good example, but if I pick the token door as my next token, maybe it's got a very likely next token after that of, say, knob, because door knob, and that will be, say, likelihood 80%. But if I pick some other word like grass, maybe there are no very likely tokens following grass and everything is 10%. So you've got 10 tokens that are 10% each. Well, if you calculate the probability of those sequences, you'll actually find that it may have been better to take a less likely next token in order to have a very likely following token. But of course, that's not going to be taken into account if you're just penalizing strictly based on the next token. So mathematically, by pulling in information on future tokens, you are allowing less information from your raw data to leak, and you're taking better advantage from your data. There's a second benefit, though, to having the ability to predict future tokens, and that's for speculative decoding. I have a video if you want to understand that in more detail. But the idea with speculative decoding is to have some kind of fast model that can predict later tokens, not just the next token. And you use those later tokens in your main model to decode in parallel. So you essentially check not just the next token, but you check your guesses for future tokens. And if those guesses are correct, you're able to accept those tokens and effectively get multiple tokens decoded at once. Now, I know that explanation is not great, but you can have a look at the video if you want to understand it in more detail. And what's important for a good speculative model, this is a model that kind of decodes ahead, so it will get future tokens in advance and faster than your main model. What's important is that it has a high accuracy, and the accuracy is very high with this next token prediction model. If we look at the acceptance rate, I can search for acceptance. The acceptance rate of tokens produced by this extra layer of the transformer is between 85 and 90%. So at the cost of just one more transformer block, and keep in mind that you have usually say 60 to 100 within your main transformer, for just adding one tiny extra bit of compute, you're able to predict future tokens with very high accuracy. And because these are almost always correct, this almost close to doubles your rate of token production. So you can deliver 1.8 times the tokens per second. So in principle, with this extra module, you can greatly accelerate your decoding speed, and you can also improve the performance of the model because you are making better use of the data that's there in the first place. So that rounds up the three different improvements that Deepseek have. Well, these are three selected improvements because I've already described the main ones, which are around making load balancing work within the mixture of experts architecture. If you've any other questions, let me know down in the comments below. That rounds up this video, and I'll put a link to any of the resources down in the description there too. So cheers, folks.